The MCAT Podcast, session number 130. A collaboration between the medical school headquarters and Next Step Test Prep, the MCAT Podcast is here to make sure you have the information you need to succeed on your MCAT test day. We all know that the MCAT is one of the biggest hurdles you'll face as a pre-med, and we're here to give you the motivation and information that you need to know to help you get the score you deserve so you can one day call yourself a physician. Welcome to the MCAT Podcast. My name is Dr. Ryan Gray, your host here every week, where I'm joined by Clara from Next Step Test Prep. And we are continuing our journey through Next Step Test Prep Full Length 10 Biochem. All right, Clara, back for some more MCAT prep with Next Step Test Prep Full Length 10. Last week we finished up our last discrete section or discrete group of questions for Full Length 10. We have two more passages for the Biochem section before we're lucky enough to move on. So, passage 9, what kind of fun things do we have in store for us today?
Oh, I'm really excited for this passage, which might be a bad sign, but yeah, so basically what we're going to cover with this one is sort of a combination of metabolism and even a little bit of like acid-base chemistry, which is actually my favorite MCAT topic ever.
Did you write this passage, Clara?
No, I did not.
Okay. I thought maybe that's why you were excited.
No, unfortunately I didn't, but I love acid-base chem, and I love when test writers can integrate it into the bio section, because that's exactly what the MCAT's going to do.
Yeah, okay.
All right, so let's see. Passage 9. Ketone bodies are molecules that are produced by the liver during times of low glucose levels. Figure 1, which we don't need, but they are talking about the structures of the three naturally occurring ketone bodies in humans: acetone, acetoacetic acid, and beta-hydroxybutyric acid. So if we imagine we had seen that figure, it would just be some chemical structures of these things.
Okay. These
ketone bodies are synthesized from acetyl-CoA. Normally in the liver, acetyl-CoA enters the Krebs cycle. However, if there's a lack of oxaloacetate or an overabundance of acetyl-CoA released from beta-oxidation of fatty acids, then the acetyl-CoA will be built into ketone bodies via ketogenesis. If acetoacetate is not used within about 5 hours of its creation, it will be decarboxylated into a metabolically inert ketone. Acetoacetate and beta-hydroxybutyrate dehydrogenase are picked up from the liver and transported to other parts of the body, where they can be converted back into acetyl-CoA and enter the Krebs cycle. The brain and heart are the biggest consumers of ketone bodies as a source of energy. A state of higher than normal ketone body levels is known as ketosis. Significantly high levels of ketone bodies will lower blood pH, a condition known as ketoacidosis. All right.
Oh, okay. So all I'm thinking about are the really buff pre-med students who are like, I'm in ketosis right now. I know I can. This is an easy question for me.
Oh, so true.
Okay. So question 48. Which of the following best explains why high blood levels of ketone bodies lower blood pH? A, because acetoacetic acid and beta-hydroxybutyric acid have pKa's above physiological pH. B, because production of ketone bodies produce CO2, which reacts with water to form carbonic acid. C, because production of ketone bodies releases coenzyme A, which is highly acidic. Or D, because acetoacetic acid and beta-hydroxybutyric acid have pKa values below physiological pH. So A and D are opposites. Mm-hmm. And then the other one, so production of CO2 with ketone bodies. I don't remember anything in the passage talking about CO2, and then specifically coenzyme A. I don't remember anything about specifically in the passage. So this makes me think that this is just something I need to know about production of ketones. outside of the passage itself. And so I'm looking at it going, if I were a betting man, I would go with A or D because they wouldn't have to. It's just silly. It's like, in my mind, test taking strategy wise, I'm like, they wouldn't have both if both of them were wrong. Why would they do that? And so I'm like, I don't know if that's the right answer, but and so, oh man, ketone bodies lower blood pH. And so two of them, they're saying, okay, these two have pKa's above physiological pH, pKa's below physiologic pH. Oh, I don't know. So not remembering the pKa's and what specifically that means, I want to say, I want to say D, but I don't know why I want to say D. I'm like, well, it's below physiologic pH, and that's how you lower it, but I don't know.
That is a good guess. That's right.
Oh man, it's so hard when you don't remember any of this stuff. But I go through this pain to hopefully just go through my thought process, which hopefully helps students.
Oh, totally. Yeah, it's valuable to be able to, even if you're like, oh, I haven't seen this content yet, to be able to see how far can you get just with reasoning.
Yeah.
And actually, your reasoning was pretty much right on here. Like, you were thinking, oh, pH, like low pH, acidic, and pKa follows that same sort of scale. Essentially, it corresponds where lower pKa corresponds to something that's more acidic, just like lower pH is more acidic.
Okay.
So here, when they say because acetoacetic acid and beta hydroxybutyric acid have pKa values below physiological pH, they're essentially saying, okay, low pKa values, these compounds are acidic. And that's exactly what the question asks. So it's essentially just saying, oh, they lower blood pH because these two ketone bodies are just literally acidic. Yeah.
Yeah. Okay.
Yeah. So A would have been backwards then. pKa is above would be less acidic. And then B and C both sort of look tempting because they involve acid in some way. But yeah, we don't need to know that kind of detail about ketone body production. So it's very likely that those answers are just not true.
Mm-hmm. Okay.
Cool. All right. The next one, 49. Would a person with diabetes be at a greater risk of developing ketoacidosis? A, yes, because lack of insulin means lack of glucose in liver cells, halting the Krebs cycle and causing an overabundance of acetyl-CoA, resulting in ketogenesis and ketoacidosis. B says no, because lack of insulin means abundance of glucose in blood, meaning there's plenty of glucose available to enter the Krebs cycle as pyruvate. C says no as well. Lack of insulin means lack of glucose in liver cells. However, the Krebs cycle will not be interrupted even without pyruvate. And then finally, D says yes, because lack of insulin means an abundance of glucose in blood, resulting in higher acetyl-CoA levels, which then undergo ketogenesis, resulting in ketoacidosis.
Ooh.
Long answers.
Yeah. And so for me, I think just from a physiological standpoint, there's a thing called diabetic ketoacidosis. And so DKA is one of the first presenting signs of somebody with diabetes or super uncontrolled diabetes. And so, yes, for me, the answer is an easy yes, because there literally is something called diabetic ketoacidosis. And so B and C are out for me. And so now the question is, what is the cause to determine if it's A or D? So lack of insulin means lack of glucose in liver cells, halting the Krebs cycle, causing an overabundance of acetyl-CoA, resulting in ketogenesis and ketoacidosis, which makes sense. D, yes, because lack of insulin means an abundance of glucose in blood, resulting in higher acetyl-CoA levels, which then undergo ketogenesis, resulting in ketoacidosis. Oh, it's hard because the first part of both of these are true. Mm-hmm. And so the question is, are the higher levels of acetyl-CoA because glucose is in the blood, or is it because the Krebs cycle stops? And going back to the question, ketone bodies are synthesized from acetyl-CoA. In the liver, acetyl-CoA enters the Krebs cycle. However, if there's a lack of oxaloacetate or an overabundance of acetyl-CoA released from beta oxidation of fatty acids, the acetyl-CoA will be built into ketone bodies via ketogenesis. Huh. And so they talk about the liver there. And so immediately I want to just answer choice A because it talks about liver cells and the Krebs cycle. But it doesn't say anything. Oh man. So the question would be, does an overabundance of glucose in the blood result in higher acetyl-CoA levels? And I don't know if that's true or not. So I'm just going to pick A because it talks about the liver and the passage talks about the liver, but I'm going to assume that it's doing that to trick me, and the answer choice is really D.
It's not tricking you.
Oh, all right.
So you're right.
Nice. Okay.
Yeah. No, I think what you did was good in sort of sticking to the cells because, you didn't know what this abundance of glucose in blood would do, but we can kind of guess what it will do in cells. And actually, this is something that I didn't think about when I first started studying for the MCAT, but actually really helped me when I realized with this sort of biochemical processes that glucose in the blood doesn't really do anything, right? It's like glucose, the whole point of insulin, is like to get...
Well, it causes atherosclerosis.
Yes, it does that. But like I feel like we always picture all these processes like glycolysis and Krebs cycle and everything just happening, but they have to happen in cells.
Yeah.
So the abundance of glucose in the blood, there's no way that will directly result in higher acetyl-CoA levels because glucose would need to be in the cells for it to go through glycolysis and make pyruvate, and then for us to progress through the Krebs cycle, or actually through pyruvate decarboxylation. So A is perfect.
Okay.
Yeah. So that was a rare case where your outside knowledge actually helped you too.
A little bit.
Yeah.
A little bit. So, I mean, my dad was a diabetic, so that was an easy one. But then also, as you go through medical school, you see a lot of DKA.
Oh, totally.
Question 50. Based on the passage, what is the most likely path for removal of acetone produced in Figure 1? And so you said we don't need the figure, so we'll remove that produced in Figure 1.
Don't.
Okay. So it's a Roman numeral 1, which we all know we love. Roman numeral 1, excretion in the urine. 2, conversion back to acetoacetate. 3, involved in anabolism of amino acids. So answer choice A is 1 only, B is 1 and 2 only, C 2 and 3 only, or D 1, 2, and 3. So how do we get rid of acetone? And it says in the passage, let's see. Picked up from the liver, transported there, done that. State of higher than normal ketone bodies. The heart and brain are biggest consumers of ketones. Acetone.
This is a hard one, I'll tell you.
Yeah, so I'm just looking. So it's funny because a lot of what the passage talks about is the acetoacetic acid and beta hydroxybutyric acid, and not necessarily acetone. So that one is like, well, you don't tell me, so how am I supposed to know? So I'm assuming it's a pseudo discrete question because of that, because they don't really tell me in the passage what happens. And so just going through conversion back to acetoacetate, I don't know, there's something that doesn't necessarily make sense to me because they all come from the acetyl-CoA. So let's see. So excreted in the urine, conversion back to acetoacetate involved in anabolism of amino acids. So making of amino acids. And so I want to say number one is true because we excrete stuff in our urine all the time, and thinking about keto sticks, right? You pee on keto sticks to see if you're in ketosis. So obviously some of that's going through urine. So I'm going to say one has to be right. And I can't say that two is wrong, because if I'm saying one is right, unless one is the only right answer, there's one only, but the other ones all have two in them. So I have to say, is it one only, or is it one and two? Building up of amino acids. I don't know what helps build amino acids. I don't think ketones would help build amino acids. So I'm going to go, but, oh man. Yeah, no. Ketones, I think. I'm going to say it's either A or B, and I'm going to go with A, one only.
Great.
Oh man, that's so hard. So I'll flush out my thinking a little bit more on that one. So the ketosis, right? I think of ketosis as we get in this state because we use it as energy. And so when I see 3 involved in anabolism of amino acids, to me that's saying it's being used as a building block for amino acids. I'm like, well, that's not right. Unless you want to really go theoretical and be like, well, the energy to create the amino acids.
Unfortunately, they don't get that.
Yeah, and so that's why I was a little hesitant. I'm like, is that what they mean? And so I stepped away from that, and that's why I got rid of 3. And then the conversion back to acetoacetate, it doesn't necessarily say that the conversion back to, it doesn't say that acetone comes from acetoacetate. So I'm like, I don't think it does. Maybe it does, but I don't think so. And that's why I stuck with 1 only.
Yeah. Yeah, I feel like there's this psychological barrier a lot of times that people have against just picking a Roman numeral with 1 only, or 2 only or 3 only. Like, we always feel like it should be more than 1, but yeah, it can totally just be one of them. And here, there are a couple different ways we could approach this. And so we're a little bit tricky here. Like, the passage doesn't directly talk about acetone, but it alludes to it in a way that we can figure out what it's talking about. So if we try to go the passage route, if we actually look at, because what you did, right? You looked through the whole passage. You didn't really see that much about acetone. Mm-hmm. But then paragraph 3 says, if acetoacetate is not used within about 5 hours of its creation, it'll be decarboxylated into a metabolically inert ketone. And acetone is a ketone. Yep. And actually and acetone is the perfect identity for what it gets decarboxylated into, because acetoacetate is, this is something where it helps to just know the structure of acetone, which I think every pre-med needs to have memorized. But acetoacetate is a pretty small molecule where essentially the only ketone we would get from it is going to be acetone. So when they're saying metabolically inert ketone, the obvious identity for that is acetone. Okay. And then if it's metabolically inert, that means it doesn't do anything in metabolism, and we just excrete it out, and that's all.
Yeah. So the conversion back is acetoacetate to acetone, not acetone to acetoacetate.
Yeah, so acetoacetate was broken down into acetone. We can't see any logical reason why acetone would get converted back into acetoacetate, because that's just converting one ketone body into another, and we can't really use these, so it doesn't make sense to convert it and then convert it back again. Yeah. Yeah, so that's out, and yeah, your reasoning for 3 was great, and also amino acids are really small. They're like these individual monomeric building blocks. We wouldn't imagine like a ketone body would be used to build these tiny little amino acids anyway. Yeah.
Oh, all right. So great. Some wonky thought processes, but we got there.
Oh yeah.
All right, there you have it. Some more biochem for you. Hopefully that was helpful. We have 2 more weeks of biochem. I hope you've been enjoying this journey, but more importantly, I hope you have been learning and taking notes along the way, so that when it comes to your MCAT day, you will have the skills, the knowledge, and the confidence necessary to get the score that you need. If you need some more help on your journey, go check out nextsteptestprep.com. Check out their one-on-one tutoring, their online course, their full-length exams, and all of the other resources that they have to offer to you, the student who needs help on your journey with the MCAT. Use the promo code MCATPOD, that's all capital letters, MCATPOD, to save some money on Next Steps resources. Hope you have a great week. We'll see you next time here for some more and the final passage for Next Step Test Prep Full Length 10 Biochem before we wrap up with the final discrete set. Have a great week.